In this section, we're going to be going over combinations. So thinking back to what we've previously done already, we know that for a permutation problem, the order is going to be important for the final outcome. So permutation's order matters. So for example, if we were taking a look at these two permutations, ABC and ACB, these represent two different permutations of the same letters because the ordering is different. If we have ABC though and ACB for a combination, this actually represents the same combination because order does not matter. So for combinations, order does not matter. Order is unimportant for combinations. Permutations, order matters. Combinations, order does not matter. So let's see an example here. Let's determine whether the situation represents a permutation or a combination. So for A, we have a group of 5 friends. Arlene, Inez, Judy, Dan, and Eunice are forming a club. The group will elect a president and a treasurer. We want to know in how many different ways can the president and the treasurer be selected. So this is going to be a permutation because we have different positions, being the president and the treasurer. So different positions represents that order matters, which means it's a permutation. For the next one, of the 5 individuals that were named previously, 2 will be attending a meeting together. We want to know how many different ways can they do this. So since no order was specified, it just says that 2 are going to be attending. That means order does not matter. So that means it's going to be a combination. Okay, so this is going to be our formula for combinations. If we are choosing R number of objects from N objects, the number of ways that we can do that is going to be N factorial divided by N minus R factorial times R factorial. So other than this R factorial, it's the same exact formula for a permutation. Essentially, we're dividing by that R factorial to divide off the permutations that were the same because they are the same exact thing for combinations, so we can't count them as individual combinations. Okay, and the way that we can read this is N choose R. So that's just kind of a short way that we can read that off. We have N total objects, and we're seeing how many different ways we can choose R objects from them. Let's do a couple examples where we're evaluating. So for the first one, we have 8 choose 3. So plugging in this formula, that's going to be 8 factorial divided by 8 minus 3 factorial times 3 factorial. And we're going to have to simplify this a little bit. So that's going to be 8 factorial divided by 5 factorial times 3 factorial. So it's a little bit messier than what we had before with permutations. But I'm going to do the similar thing that we did, and I'm going to note that the denominators are going to cancel here. And I'm going to cancel the larger number in the denominator, so I'm going to cancel that 5 factorial. So if we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is another way of saying 5 factorial. So that's going to be having the 5 factorials cancel off. 5 factorial divided by itself is 1. And we're going to end up getting 8 times 7 times 6 in the numerator. In the denominator, we still have 3 factorial. 3 factorial is 3 times 2 times 1. That's actually equal to 6. So we can cancel 6 in the numerator with that whole entire denominator. And we end up with 8 times 7. So we end up just getting 56. So there's 56 different ways to choose 3 objects from 8 objects where order does not matter. And once again, there's a button for this on the calculator under PRB, under the PRB button. Okay, let's do the next one, 10 choose 10. So plugging this in the formula, it's going to be 10 factorial divided by 10 minus 10 factorial times 10 factorial. That's going to be 10 factorial over 0 factorial times 10 factorial. 0 factorial equals 1. So that's going to be the same as 10 factorial over 10 factorial. We don't have to write times 1. So since these are the same, they actually end up canceling off, and this is just going to equal 1. So we don't even have to write anything out for this one, just recognize that they cancel. So this means that there is one way to choose 10 objects from 10 objects, which should make sense. That's just essentially gathering all 10 of those objects at once. And last one here, 5 choose 1. So for 5 choose 1, it's going to be 5 factorial over 5 minus 1 factorial times 1 factorial. And that's going to be 5 factorial over 4 factorial times 1 factorial. So for the numerator, 5 factorial we can write as 5 times 4 times 3 times 2 times 1. Or we can write that as 4 factorial. For the denominator, I'm not going to write the 1 factorial. 1 factorial is just 1, so I'm just going to leave that out. So the reason why I wrote the numerator like that was to recognize that the 4 factorials are going to cancel, and we are left with 5. So there's 5 ways to choose one object from 5 objects, which should make sense, because if we have 5 objects and we're choosing one of them, there's 5 ways to do it. It's just choosing each one individually. Okay, let's do a couple examples now. So a 3-person committee wants to be formed for a company out of 20 employees. We want to know how many different ways can we form the committee. So the order does not matter here. These employees that are being chosen for this committee don't represent any different positions. It's just a 3-person committee. There's no treasurer, president, secretary. It's just 3-person. So order does not matter, combination. So it's going to be 20 total, and we're choosing 3 of them, 3-person committee. So we're going to do 20 choose 3. That's 20 factorial over 20 minus 3 factorial times 3 factorial, which is 20 factorial over 17 factorial times 3 factorial. So we can cancel off that 17 factorial. It's going to be 20 times 19 times 18 times 17 factorial in the numerator. And that's going to be divided by 17 factorial times 3 factorial. So now we can see that the 17 factorials cancel, and we end up getting 20 times 19 times 18. 3 factorial in the denominator is 3 times 2 times 1. 3 times 2 times 1 is equal to 6. So let's just write that out. And I wrote that one out because now we can recognize that 18 divided by 6 is equal to 3. So we're left with 20 times 19 times 3. And we end up getting an answer of 1,140. So having 20 employees and choosing 3 of them for a committee, there's 1,140 different ways. Okay, so let's do a couple more examples here. So a football team wants to elect 4 captains for their offense, which consists of 11 players. We want to know how many different ways can they do this. So the order does not matter here because these are just 4 captains, so no specific other position other than just all of them being captains. So order doesn't matter, so this is a combination. So there is 11 total. We are choosing 4, so 11 choose 4. That's going to give us 11 factorial over 11 minus 4 factorial times 4 factorial, which is going to be 11 factorial over 7 factorial times 4 factorial. So let's cancel the larger number in the denominator as usual. Let's cancel 7 factorial, which means we write the numerator as 11 times 10 times 9 times 8 times 7 factorial. And now we can cancel off those 7 factorials. And then we end up getting 11 times 10 times 9 times 8 divided by 4 factorial. 4 factorial is 4 times 3 times 2 times 1. And for this right here, I'm going to cancel, so I don't have to write it out again. 4 times 2 equals 8. So 8 in the denominator cancels with 8 in the numerator. And then 9 divided by 3 equals 3. So we were left with 11 times 10 times 3 divided by 1 obviously isn't going to affect it at all. 11 times 10 times 3 gives us 330. So there's going to be 330 different ways to choose 4 objects from 11 objects. In this case, football players. Okay, let's do one more example here. So in your American history class, you're assigned to read any 3 books from a list of 8 books. We want to know in how many ways can you select 3 of the 8 books to read. So once again, order does not matter, so this is a combination. We have 8 books total. We're going to choose 3 of them. So that's going to be 8 factorial divided by 8 minus 3 factorial times 3 factorial. So 8 factorial over 5 factorial times 3 factorial. Let's cancel that 5 factorial. 8 times 7 times 6 times 5 factorial in the numerator. And we have 5 factorial divided by 5 factorial. And they cancel. We're left with 8 times 7 times 6 over 3 factorial is 3 times 2 times 1. 3 times 2 times 1 is the same as 6, so I'm going to cancel that in the numerator. We're left with 8 times 7, so we get 56. Okay, so there's 56 different possible combinations of choosing, in this case, 3 books from 8 books. Okay, so that is it for combinations.